October 17th, I'll be 100. The chemical engineering department was started September 1, 1915. And 6 weeks later, I was born. So the department thinks that we ought to celebrate the department and my birthday. It's exciting. I came from a Ukrainian family. They were unhappy with their situation at home, and everyone heard about the heaven across the Atlantic Ocean. That's what Dad called it. At that time, every coal mine had to have 100 or more coal miners, and they had none in the United States. My dad was a hard-working guy. He set the example for my brother and me. Growing up, I couldn't wait until I went to coal mines, until the first day I went in the mine, and I hated it. I couldn't stand it. It was terrible. Coal miners had to work on their belly. It was all pick and shovel. I would say once a month someone was killed. In the next room, Andy Lebowski and his dad suffered a fall. The ceiling came down, 600 feet of it, rock. It took us 3 days to find their bodies. It was heartbreaking. My brother got me a book on coal carbonization. It told how chemicals were made from coal. And the person who made chemicals from coal was called a chemical engineer. I needed a job. I didn't have any money for tuition. Every night I would write 2 or 3 letters, and it took me a couple months to get the 54 letters out. The only answer I got was the 54th letter. The president of some little school in Indiana wrote me and said, "Yes, we will admit you, and we will find a job for you somewhere on the campus." It's interesting that 25 years later, of those 54 schools, 46 of them had already made me offers to be president of their university.
As UT celebrates its centennial, it's really, in many ways, about 100 years of chemical engineering in the United States. Chemical engineering has been a discipline that's spent a lot of time evolving. The department has made that evolution over time to stay at the cutting edge. Chemical engineering is all around you. All through your daily lives, you see chemical engineering.
Coffee's made by chemical engineers. Clothing's made by chemical engineers.
Everything is a chemical of one type or the other. They're not good chemicals and bad chemicals, it's how do you use them.
It's a field that brings together all of these interesting fundamentals.
Combining chemistry and physics and math and actually even biology into understanding processes.
Literally, chemical engineering is everywhere.
Oil and gas.
Making potato chips.
Nanomaterials.
Energy efficiency.
Transportation.
Pharmaceuticals and materials.
One word, plastics.
You would be really hard-pressed to find a single product that a chemical engineer didn't have some hand in.
You need to be able to do something very innovative from a chemical perspective, but you need to be able to do it at scale.
Let's pretend that you, John, know how to make great ice cream, and the whole state of Texas falls in love with your ice cream. What do we need to actually control? Is it the same to make a little batch of ice cream versus this bigger batch? Maybe I need more energy because I need to keep this colder. Maybe I need quality control because it has to taste the same.
Chemical engineers make things at scale, they innovate, but then they have to compete in the real world, in the marketplace.
Chemical engineering is basically the heart of the business.
I think really the genius of Ventec
is this idea of modularizing chemical plants. And what they figured out is how to take that chemical plant and break it down into smaller modules that can be built in their facility in Houston and then shipped all around the world. And then when it's all put together, it works right away.
In most cases, you take a feedstock that's either crude oil or natural gas, and you process that feedstock to make a product. If it's not right, it won't work. We built one plant in Siberia. The only way you can get in is fly in. We have 2 plants in the Peruvian rainforest that are 1,800 miles up the Amazon River. You started learning certain basics while you're in college. University of Texas teaches you to think differently. We learn how to solve problems.
When I think of the University of Texas Chemical Engineering Department, I think about the giants it's had on its faculty. It has supplied a tremendous educational experience for students from its beginning. First part of the century, early 1900s, the discipline was establishing itself. It split out of chemistry, out of mechanical engineering, as a group of people who could think about processes and develop processes at massive scales to make commodity chemicals, which changed everyone's lives. Chemical engineers started making gasoline, heating oil, and ammonium nitrate for fertilizer, which transformed agriculture across the world. As the Industrial Revolution really took off, these chemicals were playing roles in our daily lives that we didn't really think about, but they were made by the ton. And as the automobile ramps up, as transportation ramps up, that demand ramps up. And the kinds of processes that you have to use to make fuel change dramatically.
The Model T Ford was introduced in 1908, and so there was a demand to create high-octane gasoline. 1914, World War I began. All of the raw chemicals and resources that we were used to importing from Europe were no longer available, and so the United States was faced with a situation where we had to fend for ourselves.
Chemical engineers started working to improve the conditions of our country so that we can better protect ourselves.
Higher education played an enormous role.
The department was founded in 1915. And the founder was Eugene P. Schock. Eugene Schock was an incredible individual. He founded the department on his own. He was the only one teaching chemical engineering courses, and at the time was really corresponding with the leaders in chemical engineering at MIT to work with them on developing the textbooks and the class materials. He really started focusing on industrial chemistry, so the application of chemistry to try to solve practical problems. After World War I and the discovery of oil at Spindletop in East Texas, the companies there were worried about wasting, and they wanted to use every bit of what you were getting out of the ground, and chemical engineering was a science that helped you to do that.
By the end of World War II, the early 50s, the discipline was developing its own identity.
I came in '46 as assistant professor. The war was over and the veterans came.
Coming out of World War II, there was this huge release of manpower, which flooded society. And with the GI Bill, they could come to universities.
At University of Texas, we went from 6,800 to 14,000 students in 1 year, and they were wonderful. They'd been overseas fighting for 4 or 5 years. They had a chip on their shoulder, and I wanted to learn, and I loved that kind of thing.
Places like the University of Texas really blossomed in that post-World War II time period. They were literally creating the alumni who were changing the world in chemical engineering over the next 50 years. The faculty had industrial experience in separations and thermodynamics, but as applied to industrial problems. And in the 1950s, they began searching for professors with different perspectives, people who were more in engineering science.
People are tired from wars. They want to have a life that is comfortable.
You were living the American dream. You had the house, the lawnmower, the 2 cars.
And this becomes the period of plastics. Polymers, that is plastics, becomes an easy compound that could be used to create articles of manufacture. from tables to chairs to this and that. We became our own economic engine, and higher education was the escalator that made that possible.
The country as a whole had an appetite for science and technology and really felt like that investments in science and technology were going to be critical if we were going to be competitive, not only economically, but also from a defense perspective.
The discipline has been fluid for a long time. That's one of the real strengths of chemical engineering. Accepting that there's these changes that are going on through the discipline in hiring faculty, teaching new courses, and letting that evolve. You could sense that when I was here in the early 70s. People teaching molecular thermodynamics and using mathematics in ways they hadn't done before.
I always felt that every faculty member must keep up to date with everything that's going around the world in his field, and then pass it on to the student.
There was a tremendous need for people with a background in polymer science.
We brought in the great Don Paul, and he opened up the whole area of polymers.
I got to see the best of both worlds. I had unit ops in the old traditional style, and at the same time I had polymer science and polymer chemistry from Don Paul, which had a big effect on me. Tom Edgar, who taught transport phenomena, had come from Princeton and was bringing that into the department.
The emergence of computers in the chemical engineering curriculum had really taken place in the 80s and the 90s, and by the time I arrived, this was one of the best places in the world to get a start in that area.
We create really a new entity, if you wish, with several professors here, with many students, who want to learn about how to address problems of control of chemical reactors, of miniaturization of processes, and so on.
We were, for the first time, being able to model materials at the molecular length scale, and I was intrigued by the idea that you could actually apply quantitative methods to design new systems from the molecule up. The thing that struck me about the professors at the university is that they held expectations extremely high, but then they were willing to provide all the resources that you needed to be successful. On the recommendation of Buddy Mullins, I took a graduate course that was taught by Roger Bonacaze. It was the best course that I ever took in my life. It was really his philosophy to bring you to the very frontier of research in the classroom, and you felt like you got there in that course.
The leadership that I've known since I've been here, it's been, folks like John McKetta, Don Paul, John Eckert, Tom Edgar. They've all been committed to the educational mission as well as our research excellence. Grant Wilson came to the department actually the same time I joined. He had already had a storied career at IBM, where he was one of the co-inventors of the chemically amplified resist. That is a material that's used to make basically every microchip that we use all the time in any computer device that we own. Grant Wilson comes to the department and he develops even better resists to make even smaller nanoscale objects. But then he is inspired and comes up with the idea for nano imprint lithography.
Academic departments have an impact on the world through two things they do: the people they educate and the research and scholarship they do. The department still has that focus. They educate great people, really first-class PhD students, and they do tremendous research. You see today faculty in the department who make things.
My research is based on nanomaterials. Specifically, we're interested in electronic materials, batteries, and especially electrochromic windows. We're developing materials that are coated onto glass that would wind up creating what we call a smart pane of glass. You can actively control the amount of light that gets transmitted. So you can change the tint in the window pane. And you can also, in our case, change the amount of heat that's transmitted from sunlight into the building. And you can do this on demand in response to changing climate conditions and just your own preferences.
I think the thing I like most about my job is that we're able to really tackle the big problems that hit people's lives.
The quality of the work is extremely important. To be in this environment, working directly with some of my colleagues to create new science that takes advantage of both of our expertise, but alone, neither of us would have the skills or the tools to do it. Most of all, I love interacting with students who are motivated and ambitious about developing their capabilities as engineers and as scientists.
The key to any department and the purpose of any department. Can you imagine what that is? The student.
And then we're also going to start working on an open system. You look at the world, you decide, well, this is going to be my system.
When you look at the graduate students and the faculty, they're not the big, scary ivory tower professors.
We want to reduce unknowns, so we know we need 2 more equations.
They're all really excited to share their stories with undergraduates, to have them involved in research in their labs.
Graduate students and undergrads work very closely together. Getting an undergrad to get hands-on experience and take command of a project and solve an open-ended problem, it's really a transformative experience. It's a totally different experience from sitting in a classroom and solving problems when they know there's an expected answer. So that's where you see the eyes sort of light up. They get involved in the research, they get involved in the design, they get involved in the outcome, in testing, and it's really wonderful to see how much that leads to their growth.
I always knew that chemical engineers change the world, but how much of the world can I really change? I was always pretty interested in science because I felt like I understood it. Chemie challenges me all the time. It's as math-intensive, chem-intensive, and physics-intensive as I expected coming in. The one thing that did surprise me was the caliber of the students. We're all going through chemie together, we're all struggling together, failing together, succeeding together. So it's a great family.
Chemical engineering at the University of Texas, I think, develops students to go out into the real world.
A lot of our undergrads are encouraged to go talk to representatives from different companies. Not only do they kind of see real corporate world or industrial world, but it also allows them to start thinking of what it is that they're interested in doing.
I had the opportunity this summer to go visit a chemical engineering company. It was a great opportunity for me to realize that everything that I'm doing has concrete meaning.
Each bay has 4 overhead bridge cranes.
But also that I can actually make a real physical impact with the work that I'm doing.
So our mission is to take landfill gas and make diesel out of it.
How does chemical engineering relate to all of that?
Oh, that's a very good question, Annie.
It was a pleasure talking to them. And you could see in their eyes that they were enjoying what they were doing.
The coolest thing is that I saw all of those boxes and lines that I drew in our problem-solving course. They're actualized, they're here. And all those problems involve these heat exchangers and pressure valves that we see, and it's right there.
We have to have chemical engineers, so if you want to stay in oil and gas, our industry needs you.
In the last couple of decades, chemical engineering became the natural place for biology and human health to start interface with engineering. Departments that were very liberal in their thinking about who they hired some faculty who were interested in healthcare and biomedical engineering.
We started focusing in on people in industry. I found out that Adam Heller was leaving Bell Labs. Almost a cold call, I basically reached out to him and said, maybe you might want to consider the University of Texas.
I came to the University of Texas for the purpose of improving the health in the U.S.
Dr. Adam Heller is an amazing guy. He has this incredible combination of an amazing intellect, boundless creativity. He started off in not great circumstances and has gone on to great things. And I think part of what drives his need or desire to make the world better is based on that experience.
It was the summer of 1944, so I was exactly 11. I remember it quite well. The Germans overthrew the Hungarian government policemen came to our home, took away our home, moved us to a brick factory where 18,000 Jews were collected in open sheds, of which all but 288, including myself, were directly locked in cattle cars and shipped to Auschwitz. All of my friends, my grandparents, were gassed and cremated. I'd never had a period in my life when I wasn't thinking about why I survived. Helping people means two things: creating products for society and transferring knowledge. Each of us is doing it in our own way. I came here with the very purpose of helping diabetic people. You can look at the disease in a very abstract way as a malfunctioning system that needs to be corrected, needs to be adjusted. And that's what I helped with. I designed the electrodes that we put in the body now to continuously monitor glucose. It's called Freestyle Libre.
I'm Ava and I'm 9. Wanna come see my room? This is my room. You can see that I like pink. I'm a girly girl and I like to play with dolls. And here is my bookshelf. I love to read.
Ava was born February 15th, the day after Valentine's Day, 2006. She's our firstborn. On September 20th, 2012, our lives changed. Ava was diagnosed with type 1 diabetes.
She just pricked my sugar and I started to scream and cry.
They did the blood sugar test and it came back high, and apparently it was so high that they wouldn't tell me. But I finally pushed and they said it's 356. And I was like, well, is that high? And they said, well, it should be around 80 to 100. And I immediately went in the bathroom and threw up because I knew what it meant. On a daily basis with type 1 diabetes, the most important thing is to check your sugar, to see if you're high or to see if you're low. If it's too high, you've got to bring the sugar down. If it's too low, you've got to bring the number up. When Ava's initially diagnosed, we did try several different meters, and we landed on the Freestyle because the Freestyle meter requires the least amount of blood. Just never let anybody else test her sugar. Ava is a force of nature. You know, when she was first diagnosed, I spent a lot of time thinking, why me? And why us? But she hasn't let it stop her or define her. She is full of life. Ava leads a completely full, normal life, and she does it because her diabetes is so well managed. And her diabetes is so well managed because the Freestyle meter makes it easy for her to test her blood sugar.
Do you think about how can I improve this reaction? But it all works toward making better lives.
Who's that old guy? I don't know him anymore. John, how are you? Give me a hug.
The power of chemical engineering is the ability to do so many different things. The mindset of a chemical engineer gives them the ability to have impacts across a broad range of fields.
If you look back over the decades, what really stands out is the impact that the faculty and the students have had in energy, in biotechnology, electronics, in design of new materials, in the environment, the things that they've done to really make life better.
The breadth of our department has changed so much. These guys are just going into nanotechnologies and all kind of areas.
It's really exciting to think about the future of chemical engineering. In the next 100 years, we'll see solutions to some of our energy crises, see development of vaccines and therapies for diseases that have been around that we've been trying to fight for so long. And I just think it's going to be a really exciting road. There are so many things that we probably don't even know chemical engineers are going to be able to solve.
We have built an incredible society, but we've got to limit CO2 emissions. We've got to work on global warming, and we've got to figure out what mitigation and adaptation looks like. If we get those problems right, the planet's going to be a wonderful place to be.
What my goal is, and I think the goal of everybody in the department, is that we provide the education and the training and the environment so that they leave with the confidence and the skills in order to make that impact that they want to on the world.
If you think about Adam Heller and you think about John Makeda, they're almost larger-than-life individuals. They had tremendous desire to overcome circumstances that they were in and to succeed, but then also to give back.
I'm 82 years old. When you're 82 years old, what's important? The only thing that's important is what you leave behind. Your students, the people whom you taught, they will change the world. This is why I'm here.